Now we start talking specifically about these quantum numbers. There's 4 of them. One of them we call electron spin. So we're going to discuss this, and we're going to discuss something called the Pauli principle. So if you don't understand the quantum model and find that very confusing, this is something you do need to know about these quantum numbers. And you can just memorize a set of rules that don't make sense, but say, that's all right, I could just execute a set of rules, kind of like playing a game. Doesn't always have to make sense. So I'm going to expect that you work on understanding these quantum numbers and then learning how to apply them. We have 4 of them. The Pauli exclusion principle says when you have more than one electron in an atom, each electron has to have a unique set of of quantum numbers, so that each electron is basically associated with that different wave function. So I might, it turns out, be able to have 2 electrons in the same orbital, but they would have to have a different spin. So when I come up with these sets of orbital numbers or quantum numbers, I'm looking for a unique set of quantum numbers for each electron in there. So when we talk about nitrogen having 7 electrons, that means each of those electrons has a different set of those 4 quantum numbers. And it's sort of like an ID card. It's sort of like, this is how I'm going to identify what this electron is tell me about what its 4 quantum numbers are. So our first quantum number is the principal quantum number is n. And this is the same n that Bohr used in his model. It's the principal quantum number, and it has something to do with the radial distribution, about how far an electron is from the nucleus. Higher numbers means it's generally farther from the nucleus. And we can talk about these things as being shells sometimes. All of the ones with a given n value are certain shells. So we have n as our starting quantum number. The next one we talk about is L, angular momentum quantum number. And the allowed values of L are dependent on what the value of n is. Complicated rules, I know, but just take it as what it is. So once you know what n is, L can be any number between 0 and 1 less than n. So let's say my n is 3. L could be 0, it could be 1, it could be 2, but it can't go up to 3 because n is 3. So I end up having a little bit fewer than what my n is. Also, the angular momentum has to do with its angular orientation. This is now when we start having angles being important. If L is 0, we're going to refer to that as an s orbital or an s subshell. If L is 1, we're going to call it a p orbital. If L is 2, we're going to call it a d orbital. If L is 3, we're going to call it an f orbital. It goes on from there, but we're not going to see many of those. So again, let's kind of look over here. Since L depends on n, if n is 1, L only has one possible value, and that's 0. Which means at the first level, I have a 1s orbital, and that's all I have. If n is 2, L could be 0 or 1. The 0, 1 is called an s orbital. The 1 is called a p orbital. If n is 3, L could be 0, 1, or 2, so I have an s and a p and a d. If n is 4, I have a spdf. We're going to talk about why I have 3 of these p and 5 of these d when we get to the next quantum number. And that's the magnetic quantum number, or called m sub L. We call it the magnetic quantum number, or ML if you want to call it that. Its values are dependent on L. So first I need to know n, then I need to know L, then I can figure out possible values of ML. And it can go from negative, its integer values from negative L up to positive L. So if L is 0, it can go from negative 0 up to 0. So it can only be 0. If L is 1, it can go from negative 1 up to positive 1. So negative 1, 0, positive 1. If L is 2, it can go negative 2, negative 1, 0, positive 1, positive 2. And that's where we start saying we start having more than one possibility of how many quantity of different orbitals. So for the s orbitals, if I can form an s orbital, I can only form one of them because the only possible ML value is 0. But it turns out I have 3 different varieties of p orbitals. one with an ml value of -1, one with an ml value of 0, one with an ml value of 1. Now when we start talking about electron configurations and further, and you may have done them in prior classes in high school before, you just cared that there were 3 of the p orbitals. But the reason why there are 3 is that one of them is a -1, one's a 0, one's a +1 in the magnetic quantum number. And with d orbitals, there'll be 5 of them because it can go from -2 to +2. So for F, I end up with 7 of them. -3 all the way up to +3. So it's always going to be 2 times the number, 2 times L plus 1 as far as the quantity that I end up getting. And these are actually describing the orientation. So we will see this when we get into looking at the shapes. I'm not going to expect you to identify them. I just need you to know what the possible values are. Spin quantum number is the last one. And the spin quantum number is referring to the direction or spin quality of the electron in an orbital. So what that ends up meaning is that you can have 2 electrons in every orbital. One with a spin up value and one with a spin down value. Sometimes we use alphas to talk about an up spin and betas to talk about a negative spin. Sometimes we just use arrows pointing up and pointing down. That's what we'll use. And the allowed values are actually +1/2 for the up value and -1/2. So I have a number associated with it, but it turns out that number is not dependent on N or on L or on ML. So every orbital can have 2 electrons in it based off the 2 different spin quantum numbers, a -1/2 or a +1/2. So now we kind of like recap our different quantum numbers. 4 quantum numbers. N kind of has to do with how far it is, and it can go integers starting at 1 on up. L has to do with its orientation. It's like how it orients, what the shape of it is. And it can go from 0 all the way up to whatever N is -1. The magnetic quantum number is dependent on L. It can go from -L up to +L. This is another way of saying -L up to +L is it can be 0, and then ±1, ±2, all the way up to ±L. So whichever way you choose to write it, it works. And then MS can be ±1/2. And so I can start with that. And again, we refer to these. You need to know that S is a code name for L is 0, P is a code name for L is 1, D is a code name for L is 2, F is a code name for L is 3. We won't really do the farther higher orbitals from that, so we continue on from there. So now I want you to try to apply it. This is the kind of stuff that you need to be able to do. So I know that some of these are a little complicated, but you know your rules about the possible values based off of N. L is dependent on what N is. ML is dependent on what L is. MS can be something different. But I want you to look and apply those rules to these set and tell me which ones of these are possible sets of quantum numbers. Follow those rules.